Yeah, that's priorities. Now, we're going to use the chain rule. I think they call it the chain rule because once you learn it, the chains of your inability to do calculus effectively are broken. There's probably another reason, but that's what I'm going with. The chain rule is super important for dealing with functions inside functions. As an example with this, okay, we have two ways of dealing with that. How can we deal with it? Could expand it and then derive each term individually, but that takes a lot of time. There are some functions we couldn't expand if I put a power there. Can anyone give me an example of a power I couldn't expand? 25. I could expand it if I had enough time. Something I just can't expand even if I've got time.
If it was a decimal?
Decimal places. So any fractional powers, any negative powers I couldn't apply that for. Cool? Does that make sense? So anytime I've got a function inside a function, and there are two representations of the chain rule, I'm going to first go through this one. This is the one given in the formula sheet. I'll explain what each of those is. Which one do you think, in this example, which one's gx?
The one inside.
The one inside, which would be?
4x squared takes 6.
4x squared minus 6. So in our example, gx would be 4x squared minus 6, which would make f dash, or fx, sorry, that to the power of the fourth power there. Cool? I'm going to go through the one on the left first because I think that makes more sense. So on the left, what we did here when we identified our gx, what we're going to do in our first line, before we do any of this, we've established that we're using the chain rule, is we're going to let u equal 4x squared minus 6. All I'm doing there is saying, look, what I've got is too challenging to deal with. I'm going to replace that with some other letter u. Are we happy with that? So now my function y, how would it read? Well, actually, before I do that, because I need to get to this point here, can I derive du dx? Am I allowed to derive du dx?
Yes.
Yep, so what would I get? Du dx equals
8x.
8x. Simple? Are we happy with that? Normally when we derive, if I've got y something x, how do I express the derivative?
You want the dx.
Now, if I had a function, I'm just trying to explain, if I had a function y equals 4x squared plus minus 6, right? How would I write the derivative of that? How would I show that I'm finding the derivative? I would write here. What would I write? I'm not going to write y. I would write dy dx, correct? In this example, what's different? I've got u, so instead of writing dy dx, I write du dx. Cool? I also have, I want you to rewrite this function here, but no x's are allowed to be written. Rewrite that function there, given what I've given you already. Given you already.
Good.
Y equals u to the power of 4, correct? So all I've done there is replace what was previously pretty tricky with something that is much more simple. Can I derive this? But it won't be dy dx, it'll be dy du. So dy du equals 4u to the power of 3. Now I want to explain how this works. So I've intentionally done that. We can ignore this for now. Just ignore what I've got here for now. So the next bit of working for this is coming up here. I want to explain the chain rule. dy dx equals du dx times dy du. Tell me how that works. How does the right hand side equal the left hand side? Tom? The du's cancel, correct? So by nature, this law is just saying, well, dy dx equals du dx times dy du, where I can cancel out my du's, correct? What am I left with on the top? What am I left with on the bottom? So I'm just breaking this problem into more manageable chunks. So now what did I have as dy? What did I have as du dx? What was du dx? 8x. So I'm going to replace du dx with 8x. Times, what was dy du? 4 times, I'm just going to write 4u to the power of 3. Am I done? What should I do?
Could you go derive even further?
I don't want to derive any further, I just want to derive it once. I could, but I don't want to derive it any further, I just want to derive it once. I'll give you a hint. These letters are important. What did my function start with? What variables did my function start with? Y's and x's, correct? What have I got now? U's, y's and x's. Can I get rid of my u? Ethan?
Would you sub back in what you let me originally?
Perfect. Let u equal whatever it was initially. 4x squared minus 6. I'm going to put brackets around that. You wouldn't normally, but why do you think I'm putting brackets here? Yeah, so that when we sub back in, we keep those brackets because we've got it to the power of 3. Okay, cool. So then my final line would be dy dx equals, I want you to write down what my final line should look like. What you think it should look like. If you got the same answer as me, give yourself a big tick. Who got that? Who got 32x, 4x squared minus 6 to the power of 3? Who got something different? Who got to this line but didn't collect the like terms? There's nothing wrong with that. Just make sure we collect the like terms. Why can't we simplify, go any further with that? Why can't we expand the 32x in?
You have to.
I have to do my cube first, correct? So I can't expand it until I got rid of my cube. Nothing wrong with leaving it in that form there. Sweet. We could derive that in a week's time, not today. Why couldn't we derive that? We could derive this part of it, correct? And we can derive this part of it. We can't do them when they're multiplying together, yet there's another rule that we'll learn to deal with multiplication. Sweet. I might hold off explaining this way. I just want you to get familiar with this technique first, then I'll explain. It's the same technique, but it just looks a bit different. I want you to jump on to question exercise 10.6 and just practice doing that technique. A reminder, our first step is we sub u in, du dx Rewrite our equation, dy du, sub in and solve. Cool? Sub in and simplify, not solve.